Hi, sorry to do this to you, but we're going to get back into piecewise functions. Those nasty Frankenstein type deals that we probably last saw in pre-calculus, where you got one function on this side, one function this side, got to put them together, right? If you don't know what I'm talking about and you haven't seen them in a while, but you have this in calculus, definitely go back and search piecewise functions on this site, or you can just go to the pre-calculus class page and look for graphing transformations and piecewise functions, which is all about, given a chunk of equations like this, how do you make a graph out of them? But you can kind of see where this is headed, because doesn't this graph, now this graph is not, by the way, not the graph, it's not the graph of this, two different things, but the point is that, see how this graph looks an awful lot like we've been doing in the limits chapter up to now? Well, that's because up to now, I've always given you the graph. And that is a type of problem where your teacher or your book or your test or whatever, they'll give you a funky looking graph and ask you, hey, what's the limit at 2? And is it continuous at 3? And all that kind of stuff. But in this case, what we're going to do is they're not going to give you the graph. They're just going to give you the crazy set of equations and piecewise junk that created that graph, and you'll have to come up with everything out of your own head. So that's what this video is about. It's about when they don't give you the graph, when they just give you the nasty set of equations, how do you figure out what the limit is and if it exists and all that kind of junk. And basically what you're going to want to do is graph them. We want to do a really great job of graphing them, but if you're totally lost in this piecewise function stuff after watching this video, then go back and find that other video in pre-calculus about piecewise functions, because it's a little bit funky. So basically the point is, just to remind you, if you do recognize these a little bit, what this is saying is the domain they're going to split in half at 2. So like everything to the left of 2 is going to have the same graph as x squared minus 1, which is like a parabola. And then everything to the right of 2 is going to have the graph of this line, negative x plus 5, which you might recognize as a slope of negative 1, whatever. And of course, the action is going to be at 2, because 2 is where we go from being a parabola to being a line. And the question is, are those going to line up, meet up, or are they going to not line up? And of course, that's the kind of stuff where like the limit either exists or it doesn't, and the function's either continuous or it's not, and all that kind of stuff. So the question is this thing continuous? Is the function continuous? Let's figure out what happens at 2. So what we'll do is we'll say, hey, you know what, to the left of 2, and including 2, so we'll put a closed dot, a filled in circle, because it also equals 2. It's just x squared minus 1, which is a parabola. I believe it has a vertex down here. But the real point is that by the time we get to 2, this parabola is going to come up and be somewhere. We need to know where that is. So what we're going to do is we're going to plug in 2 to this to find out, so it's a parabola, where's it going to stop? What's that endpoint we want to fill in? So we just plug in 2 to the formula and we get 3, because 2 squared is 4, minus 1 is 3. So that means we got the point 2 comma 3. And again, that's filled in because we have an equal sign under that less than sign. All right, so basically it's a parabola and it shoots off like that forever. But then as it comes up here, it's going to suddenly end at 2 comma 3. All right, so that's this left function. That's the first row of this piecewise function. The second row is what happens to the right of 2. At that point, it's going to become a line that's going down to the right. But where does it start? So I know I have a line going down to the right somewhere, but where's it at? Where's that starting point where the line shoots out of? So what I'm going to do is I'm going to take 2 and plug it into this function to find out what's that first point on the line. Plug in 2 to this, and you get negative 2 plus 5 is 3. Oh, look at that. That's actually the same point we already had. So this thing shoots off like this. So what does that mean? Well, since these two functions meet up, they go like this, and that elbow has a solid dot. This is a continuous function. We could draw this thing, trace it without our pencil leaving the paper. Another way of looking at it is that really technical definition of continuity that I had from the previous video was that if the limit exists, which means the left hand and the right hand limits have to be equal to each other, since they're both 3, if we approached 2 from the right, we'd be following this. Approach 2 from the left, we'd be following this, but that left hand and right hand limit, they collide right at that point 2 comma 3. So they both have a limit of 3, and therefore it's continuous, and the limit exists and everything. Bingo. So it's continuous. So that's what happens if at that junction point, in this case x equals 2, if that meets up properly, we got a continuous function. What happens though if they don't match up? I don't know, maybe this problem will show us. Alright, so is it continuous on the interval negative 1 to infinity? Now this might seem kind of random, but basically the reason I said negative 1 to infinity instead of all real numbers is because anything less than -1, like -2, you plug that in for x, and this function won't exist anymore. Because -2 plus 1 is -1, you can't take the square root of a negative. You can only take the square root of a negative and get like an imaginary number, I or something, in Algebra 2. So like one chapter of Algebra 2, you're allowed to do that. Never again, pretty much, are you allowed to do that. So that's why we had to start at -1. We couldn't go to the left of -1 because the square root function thing does not exist. So now we just want to graph stuff. Looks like the key point is 3, because this one, greater than 3, you got this function. Less than 3, you got this function. So 3 is where the action is. So what I'm going to do is I got to plug in 3 to each of my functions. So if I plug in 3 to this function, I get square root of 4, which is 2. So at 3, I got a y value of 2. And is that an open or closed dot? Well, let's see. It's closed because we have an equal sign under the greater than, or the less than symbol right there. So that's the point at 3, and then it was a square root function, right? So maybe it comes back like this or something. I don't know. Doesn't really matter for this problem. All we care about is what's going to happen at that handoff point where the two Frankenstein arms get stuck together. So now to figure out what's going on with my other function that's going to shoot off to the right, the other direction, I got to plug in 3 to the other function. So 3 squared is 9 minus 4 is 5. So that gave me the point 3 comma 5 for this bottom function. So 3 and then 1, 2, 3, 4, 5. Right here. Now is that an open or closed dot? Should I color this in? Well, it's actually an open dot because I have greater than, not greater than or equal to, which means that it's an open dot. And then it's going to shoot off x squared minus 4. Again, I think that's a parabola type situation, so it goes off something like that. I don't know. It doesn't even matter because you can see the damage has already been done. These two did not meet up together. There's a gap. Right here, there's a distressing gap between the two dots, and therefore this thing is not continuous. So no. And then what about limits? So let's just take a second to get a little bit of practice with limits, even though they didn't ask it. What's the limit of this function as x approaches 3 from the left? Well, approaching 3 from the left, we're going to be on this puppy, driving along the road towards the limit. Looks like we're headed for this point, which is 2. So the limit as x approaches 3 from the left is 2. What about the limit as x approaches 3 from the right? That's a plus sign to the right side of the 3. Well, let's see. If I'm approaching 3 from the right, I'm actually not on this road anymore. I'm on this road up here. And I'm driving that direction down towards that open dot. And just before I get to that open dot, it looks like I'm headed for that dot, which is 3 comma 5. So the limit as approach 3 from the right is 5. So those two limits exist. But what about the limit as x just approaches 3? Now this time I didn't put a plus or minus next to it. It's just 3. So what that means is the limit from the left and right have to match. But they don't. We've got a limit of 5 coming from the right. You know, this 5 and this 2 are not equal to each other. And since they're not equal, these things don't line up. Therefore, the limit as x approaches 3 does not exist. Because they have to match up. If that's still not clear at all, then go back and watch the couple videos ago about does my limit exist or not. All right, three-way crazy. There's just the hardest piecewise functions are the ones where they give you 3 lines instead of 2. So just got to go through, figure it out. Looks like all the action's going to happen at 2. Because these are just a bunch of regular functions. The only weirdness is there's going to be a handoff where this is stuck to this, is stuck to this. All 3 things get stuck together at 2. So let's just take a crack. First thing I do is my top line, I plug in 2 to this thing and I get 5, right? So that means the point 2 comma 5 is on the graph of the first one. Now is that a closed dot or open dot? Well, there's no equal sign under that less than 2. It's not less than or equal to 2. It's open dot. And then go to the left, looks like a parabola. So maybe it's something like that. I don't know, who cares, doesn't matter. What we care about is what happens at 2. The left, not so much. All right, so then we got at 2. So what happens at 2? Well, let's see. At 2, we got 2. So that's weird. This middle line of the function is only giving us the point 2 comma 2. Seriously weird. So that is right here. And then this last line accounts for everything else. Everything to the right of 2 is negative x plus 7. So what we're going to do is just to figure out what happens at the handoff point when the baton is being passed from the left function to the right function, It's going to be at x equals 2, so we'll plug in 2 and we get negative 2 plus 7 is 5. Oh look, that's the same point right here we got before. And once again, it's not greater than or equal to 2, it's just greater than. There's no equal sign in there. So it's an open dot again. So basically, we already had an open dot right here. And now we're going to have another open dot on top of it, but really we don't need to draw it because one open dot is as good as 2. So we got an open dot, and at that point we've got a line with a slope of negative 1 shooting off here. Now again, it doesn't matter how pretty this is. All that matters is we have something, I guess this way, shooting off to the right from that open dot. So you can see that now, through all these weird equations, this piecewise function junk, we've actually got a picture that looks exactly what I was looking at and showing you guys in the graphical limits video, right? This is what we've been looking at for a while now, left-sided, right-sided limits, all that kind of stuff. So this should be old hat by now. But basically look at this and you say, like, is this a continuous function? Well, no, because we talked about how if there's a missing point in the middle of the line, it's not a continuous function, it just isn't. So it's not continuous. However, you might ask yourself, does the limit exist at 2? So is there a limit as x approaches 2? There's not 2 from the right or 2 from the left, just does the limit exist as you approach 2? Well, yeah, it does, because the left and the right both come together at the same point. That open dot was a limit for both sides. So that just equals 5, and it exists, obviously, if it's 5. Does not exist. The limit as x approaches 2 from the left is also going to equal 5, and the limit as x approaches 2 from the right, meaning a plus sign next to it, is also equal to 5. So all three things agree. What about f of 2? What is that? Well, f of 2 is just if you plug in 2 to a function, what do you get? If you plug in 2, that's this one, right? Because the only one of these three lines that accounts for x equaling 2 is the second line, and that says, hey, if x equals 2, y is 2. So f of 2 is 2. Pretty wacky stuff, right? And these piecewise functions, like I said, they're nasty. If you think you're in a hard AP class or a hard college class, there's a decent chance you're going to get one of these piecewise functions on the test, and you'll have to sort of do all this manually. If you have an easier class or in your regular calculus, then there's a decent chance that you'll really barely have to do this stuff, and you're more likely to get sort of like multiple choice questions, or your teacher will just draw the graph for you on the test and then ask you about the different points and stuff. Because a lot of teachers know that this graphing piecewise stuff is really hard for students. So if they're a sort of nicer teacher that's not trying to totally burn you, then they'll do the drawing for you to spare you the trouble of having to graph them, because these can be rough. All right, so that's pretty much it for graphical limits and for like basic limit stuff. In the next chapter, we're going to get into analytical limits, which is where there's not going to be any graphs involved. It's just going to be a lot of algebra, a lot of rules and strategies. It's kind of like trig proofs or something. But that'll be some hardcore calculus where you're just basically taking really complicated looking problems and simplifying them and trying stuff in order to get that limit to exist.